Okay, so I'm gonna be going over basic FEA stuff. So really, the two types of FEA that we primarily use. Nothing really complicated right now. We can always go over more complicated stuff later. You can always message me or Zony or Red. Um, we've done more complicated stuff, and it's more stuff that's geared towards specific items, so it's not necessarily applicable for everyone. So I'm just going to go over like the basic ones for now, and it's going to be 30 minutes, I think. So, um, so the first thing when you're looking at your part and what you want to analyze is you want to determine what you're trying to meet, like what kind of goal you have for your part. So like maybe you want to compare your part to an old one, like so you're making a brand new part and you want your new part to be as strong as your old part because you know that old one was strong. So for instance, our control arms, we had to change the shape of the control arms, and we had the goal of making them as strong as the last one. You might also have some theoretical forces that you want to meet. So like you have a completely new part, and you have a theoretical force, like rated force that you want, or you have or like you did calculations to determine what forces you need, and you want to meet that goal. Or the third option would be you had a part that failed, and you want to exceed uh, the strength of that part, or you did. Typically, you would also have done testing to determine where that part failed, like what force that part failed at, and what stress and strain it was experiencing, and then you want your new part to be to meet those new goals, rather than just meet what the old one was. Um, so typically, you want to look at your part and say, okay, where. So once you determine whichever part you're gonna improve, so for instance, we're gonna take the lower control arm here. Um, so you're gonna want to look at where it's connected to other things. So here it's connected to the frame here on hinges, and then to the ball joint over here. So there's a ball joint that sits in the cup here. So you want to look at where it's connected to everything, because that's where all the forces are going to be occurring, right? And then that also determines how it's going to move, and that's going to determine more things about what you need to set in your analysis. So typically, the best way to do this is to go one part at a time. You can technically do an FEA on an entire assembly, but that's not really recommended because it gets a lot more complicated. And oh, does it? Oh, okay. So I didn't put the whole assembly in there. I'm just showing you the whole assembly right now. Yeah. Those are example parts. Yeah. Yeah. I'm gonna get those in a second. This is just for demonstration's sake. But yeah. So um, okay. Oh yeah. So SolidWorks does have a feature that lets you take an assembly, run it through an FEA, and then like you can specify specific parts and like say like okay, I need this one to be like you can change the settings for each part, but that's like way high level. And so basically right now you're just focusing on I have this specific part. I'm going to do an FEA on this part that represents the forces that other parts are uh, putting on it. So I'm going to start by doing, actually, I'm going to leave this up for now. Yeah, I'm going to start with the simplest one, I think, which is going to be a beam analysis. So this is the lower control arm that I was just showing you before. So like I said, these two hinges here, this is where it connects to the car on the inboard side, and then this cup here is where it connects to the ball joint on these two sides. So to start your FEA, you're going to need to have your simulation window up here, the simulation toolbar. In order to get that, you're going to have to right click and go to toolbars, make sure it's checked off. Yeah, if it's not, it's right here. Is everyone good so far? If you're following along. If anyone's not, well, like if you need me to slow down or anything, I can. Okay, I'm gonna keep going then. Okay, so you're gonna go to simulation. Oh. Thank you, Phil. You're gonna go to simulation, and then up here, new study. So it's gonna give you a bunch of different options like static, frequency, topology, design study, all these different types of things. We're gonna focus on static for right now. So that's your basic basic FEA, pretty much for forces and things like that. Other ones you might use would be like thermal. Thermal, I think brakes uses thermal for determining like heat characteristics of the rotors. And I think chassis uses frequency for the frame, right? But yeah, you could also use buckling fatigue, but that's a bit higher level. So then usually I will name my file something like, so I'll do like, yours does not have your simulation. Okay, so you want to go up to right click your toolbar and then go to toolbars. Does that work? Okay, I'll wait. Oh, but yeah, in the meantime, I usually put a name on it that's like representative of what I'm doing, so I'll put like beam. Okay. I won't go too far. I won't go too far. So I'll do like beam, and if I know like the direction of the force I'm going to apply to it, I'll put like the name of the force, and I'll leave parentheses for. So I usually put the eventual results in the title of it because, as you'll see in a second, they come up on the bottom. Oh, I already have this one in here, so gotta get. I'll just make it a different one. Make it -x. So I usually do that. So now you're in the simulation mode. Okay. So then you're gonna have this little tree down here. So the first thing I usually do is I go into properties and I change the incompatible bending options. I'll do simplified, just because that's usually just the standard option we use. It's automatic will probably pick simplified. More accurate is, as it says, slower, and it does more points. It works slightly different with nodes and things like that, but that's again a bit higher level. And then we do automatic solver, and use in plane and use soft spring. We've just found that these two settings make it make the results more consistent. I have tested it without these other two, and it's not a huge difference. So I think it does depend on the model, but those are just the safe options we use. Your toolbar does not have simulations. I'm not sure what that. Wait. So like you right click and it doesn't come up at all? Oh, okay, that's interesting. Wait, does anyone else with the version we sent out to new members have simulation working? Is it maybe the new member one? That's interesting. Does anyone else know why that might be happening? Because I don't know. Is it possible that their version doesn't have it? The gear on top. Oh, yes, maybe. There might have been, yeah. There might have been something you had to click, but it's usually automatically clicked. Oh, that's interesting. Wait, Red, can you pause the record? Okay. So like I said, the first step I usually go to is properties, and I'll go to simplified, and then automatic solver selection, in plane effect, and soft spring. It's not really important right now why we do that, but it makes the model simpler, and we've tested it a little bit. The next thing I go to is I make sure that all of the bodies have a material. So sometimes when you make a model, you might forget to add a material to it. In order to do an FEA simulation, you need to make sure that it has a model, otherwise it has no idea what kind of properties your part has. So this one's already got one, but it's 4130 still. So like I actually have favorites here. So you can put favorites in this menu, but you can also go here and it'll show you, you can come to this menu and then pick out whatever material you have and apply it. And then the next thing is you select what kind of body each of your sections of your part are. So each of these parts of the control arm is a different body essentially, and it will kind of analyze different types of bodies in a different way. So these weldments, which are like basically just tubes, they'll be analyzed different from this cup. So these tubes are called, at the moment, they're modeled as beams, and that's the proper way to model anything that's a tube type structure, something, or there's something called a weldment, which is usually how you make a tube. But the basic method of the automatic kind of method of FEA would be to use solid body. I'll go over that next, but I think this is a bit more. This is what I want to go over first, though. So for beams and everything, you want to make sure that they have this little beam, this little I-beam icon next to them. You can always just check by right-clicking them, and it'll say if it says treat as solid, that means it's already a beam. But you can technically mix solids and beams in an FEA, but it's not going to come out right. So in order to do the proper thing, you have to simplify your model. And to simplify your model, you have to remove things that aren't going to be modeled properly. So like these little tubes here, they're too short to be modeled as beams, and they're not going to come out properly. I can show you what happens if you try to model those as beams. And also this cup. See, this cup is actually, if you see the little like weird shape here, that means it's a solid body. So that means that has to be excluded. So if you want it, so if you want something to not be part of the FEA without having to like physically remove it from your model, you can do it it'll only affect the model while it's in the FEA. So you can right click and go exclude from analysis. So that just kind of makes it disappear. You can actually see what everything else looks like that was there. And then the next thing I'm going to exclude would be these two end pieces here. So then you can just click on them here and then exclude from analysis. Oh, other kind of shortcut. For trees, if you want to expand the entire tree, you can click on it and then click the star button on your keyboard and the whole thing just pops down. So, all right, next thing, joint group, I don't touch that because I don't need to. And you probably shouldn't need to either because the joints are already kind of set up by themselves. So the next thing though is going to be fixtures. So fixtures are your constraints and what kind of keep the model, what limits the model from moving in certain directions. For beams, it's pretty limited. It's just fixed geometry, immovable, and use reference geometry. So I'm just going to use fixed geometry for now. And so to kind of apply things on a beam, you got to have these little dots. And each of these little dots is called a joint. So in order to apply it, you click, make sure this is selected, this little blue box over here, and then you come to each one and you click it. It'll pop up over here, and you come over here and you select the other joint. So now these two hinges essentially are now just locked. And I'm not treating them as hinges because I really can't in this model, and it also simplifies it to just the specific directions of forces. I don't really need to model if it rotates right now. Okay. So the next thing would be to apply a force. So I have a question for everyone actually. So based on kind of, I guess, basic understanding of the movement. So the suspension moves up and down kind of like a sweeping motion, right? And then it also experiences forces from the road and from different types of angles of the suspension, things like that. What directions do you guys think the forces should be applied? anyone can answer if you want. Or like okay, let's start with an easy one. Where should the forces be applied? We already have, so we have the first 2 points of contact here with the frame are the hinges. We already did those two. Those are constrained to be non-moving. Earlier I had mentioned that there's a third one that's connecting to something else that should also be analyzed, I guess, and where the force would be located. So where should we apply a force to in the model? Okay, so we're going to apply a force at the cup because that's where the ball joint is. So anything, in order for a force to get to the control arm, it either has to go through the frame, through the hinges, or it has to go through the ball joint to the cup. So since we already have the hinges declared as fixed, we now make the final one, the cup, as the location of the force. So we come back here and came off of the thing. Okay, so we already have. Oh, I have my planes here. Okay, so we have the place where the cup was, and now it's represented by this joint. So in order to represent the force, we're going to need to apply the force to that joint. But we need to be able to apply it in a certain direction. So actually, one direction is, two directions are actually already good to go. So I'm just going to do those two for the moment. So you get multiple different options for what you can apply a force to. You can go to vertices or points. You can go to a joint, which is what I'm going to pick, or you can go to a whole entire beam. So you could pick a whole beam and say you want to apply it to that whole beam. But I'm going to go to this joint here. So the next thing that you can pick is the thing that's going to be your reference point for your like the direction of your force. So you can pick a face, or you can pick a plane. I usually pick a plane because it's pretty straightforward as to where it can. It's just the easiest in my opinion. And then I will change the units to American, and then it will start. And then once, oh, okay, sorry. And in the force menu here, you want to click. You can click each of these to see. This will click on this button activates that as your direction of your force. So when you click each one, it'll put a little arrow on it to show you which direction it's moving in. So what I'm going to want is side to side, right? Because the control arms will be loaded in a like longitudinal kind of direction. So initially it's just going to give you some arbitrary kind of number here, but I'm just going to make that, I don't know, say 2,000 for now. That's going to be 2,000 pound force. So now we have constraints that limit motion in the hinges, and we also have a force here, and it should be pretty much fully defined at this point. Now, the next thing to do would be to create a mesh. So with beams, it's really, really, really simple. There's no mesh settings to change. It makes a mesh automatically for you. So you just click on the mesh, and then you go to create mesh, and it does it. So for a beam, it'll make these kind of like tubular kind of sections for a mesh. This is a bit different from what a solid body mesh would be, but this is just kind of what it does, and that's why it works best with tubes. So now this is actually all good to go for you to run the simulation. So to run the simulation, you come up here to run this study, and you can just click the button, and it'll do it. And beams are really nice because they're really, really fast most of the time. If your simulation is going really slow for like a small, simple model, it's probably not going to work right. But so what you get is you get this deformed result actually. You get these colors on the part that represent the stress on the part in those different locations. So, and then on the side here is your scale, and usually you'll have like a goal. So you want to see. So for instance, what I do is I try to increase the force that I applied until I hit yield stress, and it'll tell you the yield strength down here. So I will go until I see that at the very top here. Like that's like the max that anything hits. Because that's just what, because all of my parts have usually just been like, I want to find what the rated load is. So so right now we're actually below the yield strength by a pretty decent bit. So like we're at like we want 4.6 times 10 to the 8. We're at like 2.7 something. So the next thing I would do, I'd go back to force, and I would pick something. I would pick something like somewhat higher. So the method I use to find this force, there's no method, at least that I know of, that'll just find this number for you. So you kind of have to search for it yourself. So you're gonna learn about this in 320, but it's called the bisection method. So you're gonna want to go higher, like higher than where you think it's gonna be, and you want to go like start low and start high, and then kind of keep taking the midpoint, and then if you find the midpoint is too low, then you go up, and then you just kind of keep iterating. I'll show you in a second. So I started with 2,000. I'm gonna try, I don't know, 4,000, and see what the results are. Okay, so this is beyond the yield strength right now. So since so now I want to go exactly in half between those two, so I'm gonna go like 3,000. Okay, so this is this is below the yield strength, so now I know I can go between 3,000 and 4,000. So then I'm going to go 3,500. Okay, so that's a little bit too high. So I'm going to drop that down to 3,250 because that's in the middle. Okay, that's a little low. So I'm going to go up a bit to like 3,400. I don't know. You don't have to like do the exact bisection method, but you can. Okay, so I'm pretty close. Usually I get it to like 4.60 or 4.59. But I'm not gonna kind of keep going through this unless anyone has questions as to what I'm doing. Oh, yeah. Any questions so far? If anything's not clear. Okay. So that's kind of basically how you do the beam analysis. Oh, so like the next thing I would do is, since I found this, it's not actually the number I would use, but once I find my number, I'll put it in 3,400 here, just so that way, if you look at the file explorer for this, it will put, actually, I already have a FEA results thing, but so it'll put your results in here like this, and it'll put the title of the test that you did. So if you have like random names for your tests, you're not going to understand what it is in the menu. Another important note, these results can get kind of messy in the basic format, because typically the results will just kind of pour into wherever your file is. So if you want your results to go to a specific spot, you have to go to simulation, and then options, and then default options, results, and then you want to click under subfolder and then just type FEA results. What that does is it'll go to the same folder. So within the folder that your part's in, it'll make a subfolder called FEA results, and it'll just put all the results there. Because otherwise, you're going to have, so just imagine I had all of these in this folder. It's a complete mess. Like, you won't be able to find anything in the folder, and then you're going to want to delete it. It's just annoying. So put the stuff, tell it to put the stuff in a specific folder. You'll thank me later. Yeah, so that's basically the beam. There's a bit more to it, but you can always ask me questions, and I think I have Nikita and I have pretty decent other tutorials as to how to do a little bit higher tier stuff. So the next thing I want to do is I want to do a solid body mesh, which I'm going to do on this part. So this part is for the trailing arm, and I'm going to show that to you in a second. I need to open up. Oh, I don't have it open. There we go. So, any questions so far? I figured, yeah, I already asked that, but there are any questions? Okay. So the part that I'm looking to work on right now is this thing right here. So this connects the trailing arm to the body, and it connects. Usually there's a ball joint in here, but we removed it because it was a little unstable for the model. But this is the part we're going to work on right now. It's a very small part, and it's not a tubular structure, so it can be used for, it's better to use a solid body mesh for this one. So we're going to do that now. So the things that I would be looking at here would be, where is it connected to other things? So it's connected to the ball joint, which then connects it to this, to the tabs here, so it hinges on that ball joint, and then it's also connected to the trailing arm here. And you can't really see how it's connected, but it is, I believe, welded in, right? Yeah, it is welded to the trailing arm on this line. So we're going to go back to the port, and then so this does not have the ball joint in it. It does not have the tube that was right next to it here. So first thing, again, we're going to go to New Study, and we go to that's it. We're going to name it Solid, and then let's call it, I don't know, Test 1. I don't really have a good name for this one right now because I don't know exactly which one I want to do at the moment. So again, first thing you want to do, go to Properties, and then Simplified, use In-Plane Effect, use Soft Spring Model. Okay, and this, I believe, this one already has a material you can see up here, so that's good. It's only one body, so see it has the body symbol here. It's a body, so we're going to do a body mesh on it. Fixtures. So I'm going to say it has a fixed hinge for now. Yeah, I'm gonna call it fixed hinge for simplicity, right there. Okay, so now that's going to be this would now only rotate in that kind of direction, like around that hole. So now the next thing I'll go to is forces. So I want to apply a force where it's connected to the trailing arm. So it would theoretically be welded along this edge. So then I'm just going to do something kind of simple and say, I'm going to take that one. Let's see, maybe these edges too. Okay, so we're just going to take those edges for now and say that that's where the force is going to be, like, pulling on the part. So then the next thing would be so by default it's just going to go normal to that face. So it's going to apply these forces in the directions that those arrows are facing in. And that's not what you want, unless well, at least for this. So we want we're gonna act like the trailing arm is pulling on this part. So it's pulling like in this, like, left to right, basically, if you look at it, like we're gonna think like that. So the direction I want it to be in is gonna be in that. I'm gonna use the bottom of it as a reference frame if I can. Okay, yeah, I can. So I'm gonna use this face as the reference to where I want it to be. So the next setting you're gonna look at. So by default, it says like every selection that you made is going to apply whatever force that you put in down here. It's going to apply that to, like, separately to every single face. What you actually want is you want to have a total force, so it'll, like, distribute the force out among all of those faces. So that's what total does. And then again to English units, and then okay. So now we're gonna figure out which direction we want the force to be in. Okay, so I'm gonna take this one right? Because it's the same direction that we wanted, except it's in the opposite direction that I would like it to be. So then what I click is reverse direction. Okay, and then so I'm gonna pick another arbitrary value. I'll say 500. Okay, so that's all set up. So now the next thing you do is you go to the mesh, you go create mesh, and then you can pick coarse or fine. So the way that these meshes work is to make these like a solid body mesh will take little pyramids and pretty much make the whole part out of these little pyramids. Whereas the beam one made it out of like those tubes that you saw, kind of like stripes. This will make it out of these little pyramids. So this will determine how tiny or how big these pyramids are. Obviously, like smaller ones will be more accurate, but a bigger one will be faster. And the common issue with these solid body ones is they take too long, or certain elements might not, like certain parts of it might not be as precise as you want them to be. So like maybe in a curve, it won't represent certain things properly, depending on how coarse or fine it is. Especially if the entire part uses the same like coarseness of the mesh. Because like a flat face would need a different coarseness, right? So I'm just gonna move it a little bit over there. And mesh parameters, I'm gonna do blended curvature for now because we have these curves in it, and I want to make sure that works. Okay. Jacobian points I don't really mess with. Okay. So let's see how that mesh turns out. Okay. So there's a couple ways to kind of analyze how good your mesh is. Where'd they go? Alright, they are not here. Oh, wait, nope. Why are they not here? Alright, I'm gonna run the study and see if they come up then. Excessive displacements. Okay, so this is a message that means that something is not correct. So I'm gonna cancel that because that means the results are gonna be kind of crazy and too high. So I'm gonna just drop the force for a bit. Yeah, it's not letting me right click it. Did I break it? Yeah, it's broken. Okay. I guess I gotta wait for it for a second. Okay. So. Since this one's acting weird, I'm actually gonna show you a better example that I prefer to show. I'm actually gonna do the same thing, but to the control arm, because this is important to kind of see what happens if you do a solid body when you should be doing a beam. So I'm just gonna do that. So, got a new stuff. I'm just gonna kind of speed run through the things I already showed you. And then climate material. Okay, so for this one, I'm gonna select all of them and make them all solid bodies. Again, this is just for demonstration as to what happens when you do something. This is like partially to show you how a solid body works, and partially to show you why you shouldn't use a solid body on a tubular structure. Okay, so then fixtures. So for a solid body, you have a lot more selections available for fixtures. So with this one, you can actually pick fixed hinge. So you can go and select the inside of the tubes, the pivot tubes, which I showed you before, were the things that allow the control arm to rotate on the, against the chassis. And now those can be fixed hinges. So what that's going to do is it's going to allow, as you can see in this picture, it's going to allow it to move a bit. So the next thing I would do is I kind of want to limit the cup from moving anywhere other than just side to side. So what I'm going to do is I'm going to give it a roller slider. And I'm going to apply that to this face and this face. And now that can only go side to side as it on that plane that I just made with that. So next thing, we gotta make a force, and then so with this, I can select these faces. So the faces that the ball joint would sit on would be this one and this one. That's where it makes most of its connection to. So then again, a normal direction would apply the force outwards to all of the sorry. Okay. So it would apply that force outwards on all those faces in all directions. So since it's a circle, it'd be in every direction. So, but what we want is we want it to be left to right. Yeah, anti-voice correctors. Um, yeah, iced tea. Um, so we want it to go in all directions. I mean, no, I'm sorry, we don't want it to go in all directions. We just want it to go to the left. So what we want to do is we want to click select the direction, and then so we can just use the plane right here, and then as our reference point. And then again we're going to do total because otherwise, if I did per item and then I clicked like 1,000 here, it would put 1,000 on this upper ring and then 1,000 also on this lower ring. But what we want to do is we want to have just 1,000 in total. So we want to have total. Okay, so little arrows are going to the left, and then it converted my 1,000 into 224. Pick a number, and then click OK. So for mesh, I'm going to create the mesh, and then I'm going to leave that as is. Go to mesh parameters, blended curvature mesh, because it's a curvy feature. And so like a standard mesh would typically use the same kind of the same coarseness of the little tetrahedron pyramid things all over, but the curvature and the blend curvature will be able to change itself more towards for curved items. In advanced, I'm going to do remesh failed parts with incompatible mesh. I'm going to leave Jacobian for now, and then I'm going to click mesh, and hopefully it should work. See, it doesn't it takes a bit longer to mesh this. Yeah. So, okay. And then I'm going to run the study and see what it says. Okay. So, I want to see. Why doesn't it? Oh, here we go. Details. So, the thing that you want to analyze with details, with a solid body mesh, wow, it really didn't expand. Okay. I don't know if this is able to be read, but so for a solid body mesh, you want to look at percentage of elements with an aspect ratio less than 3. You want this to be like 90, and it's 12. So that's a big sign that you're using the wrong that you shouldn't be using solid body on this item. And then so again, for percentage of greater than 10, it should be less than 90, or I mean less than 10, right? Optimally. So that's a big no-no for doing this, and that's a big sign that like you're doing the wrong one. And typically you might actually get other types of error messages that'll tell you like, oh, your aspect ratio is too high, or things like that. I'm going to include these on a PowerPoint that I'm going to send out afterwards with some of these, with some of like the little details and things. Yeah. So I'm gonna iterate through to see what kind of force we get out of this. So let's just try 3400 and see if it's the same. I kind of doubt it. Okay, so it does not register the same kind of forces. Admittedly, the constraints are not exactly the same, but they should be relatively similar. But it is not reading the same kind of force. I want to see what it actually gives us. So if I do like 1500. Okay, so it's like, yeah, it's gonna be like 2500 or something. Yeah, okay. So, but yeah, that's basically just how you do those two. I kind of want to just take a quick crack at this because I don't know what I did. I didn't understand what I did wrong because I should not have had any issues with this. Might have just made the force too high. Yeah, okay. I did something wacky with this. Edit definition. Just make it fixed. Not try that. Okay, yeah, that worked. Okay. So it didn't like the fixed hinge on the inside of that hole. Wait. The only way to wait. Somewhere. What do you mean configuration? Oh, so the question is if you aren't sure if the part should be a beam, solid body is the only way to determine it by trying with each configuration. Oh, I mean that's one way to do it. Um, so certain things. So if you have like a cube, that's just gonna be solid body. If you have something that's a weldment or a tube, that's going to be a a beam. Or there's also a rule where if it's I think if it's wider than it is long, then that's going to be a solid body. And if it's longer than it is wide, then it can be a beam, but that's not exactly a set rule. There's also a third type, it's called a shell, which is something that's actually something I haven't done, so I can't really speak on it too much, but that's a third option. Um, actually have that here. So yeah, but um, yeah, but yeah. So it didn't like the fixed. Wait. Oh, otherwise, I don't know if I answered your question enough, but so if you want to run a solid body test, it's yeah. So basically, with the solid body test, you do have, well, in really any test, you have to try to determine if it's good because it's just a simulation, so it can be bad or it can misread something. So like, there's a lot of little settings you can tweak depending on what your part is, which is why it's kind of hard to kind of have uh, uh, an explanation as to how to do FEA in anything. But it's once you know the basics, it's kind of like you take the basics and you apply it to you start with the basics, and then if your part has some kind of weird geometry where you see like, oh, why is there this like red spot on this corner here or something, like I know just based on like my knowledge of forces and uh like 260 and stuff that like that shouldn't be there. So if if you see something that doesn't make any sense, you might want to check it out. And there's a bunch of little tools to kind of determine if your results are like good. Like I showed the details, like the details. Well, like if you get certain error messages, it'll throw up certain error messages and kind of give you hints as to like, hey, you shouldn't be doing this like in this way. Um, but yeah, so like on this one, you can see the percentage of elements with an aspect ratio less than 3 is like 97.2, and that's good. That means that the solid body worked on this. Um, whereas on the other one it didn't. So for this one, it works fine, at least in theory. Um, but again, as I said in the first lesson I gave, like if you do FEA on something, you have to have a way to test in real life, or like you have to have some kind of results, like real world results. Otherwise, it doesn't mean anything because you can run it through whatever test. You can run any part through any test you want, and it doesn't matter what results you get really, if you don't have something to prove it with, because this is just a computer thing, you know. But yeah, oh, most important thing, uh, once you're once you're done with this, you have to go and record it. Because if you don't record what you're doing, it doesn't matter. So this is one of the more recent ones I did. So I usually make a sheet, and so on the first page of the sheet, this is actually the first time I did this. I think it works pretty well. So I put my procedures to what, like, the settings I used, my instructions, so that way if someone else comes back and sees and wants to do the same thing that I did, like sees my results and says, okay, what did you do with this part? I want to do it again, or I want to validate it. You know, you could see exactly what I did, like all the steps and things like that, to see how to do it. And then I took the results and I put them in little charts for other people to read. And I tried to find specific things with this. This was a little complicated, but and then sometimes I'll also put like pictures and things in it too to show. Yeah, so I'll put like pictures in it to show like what the model looked like. I actually have this pretty. Yeah, so this was a different test I did on the same part actually. But so like for the good example of this would be the control arms. I did a lot of these. I did full results on these for the control arms, and then I also linked them to the front so you can compare all the results together. I don't know. Any questions? That's pretty much it. But oh, um, oh yeah. Also, I have like I said a couple of times, within the suspension folder. If you go to like suspension and then I think it's yeah FEA procedures. There's a whole bunch of different documents in here that show you how to do FEA and stuff. So I don't know, Red, if you want to stop the recording. That's about it. Or we can ask people can ask questions if they want.